Everyone see that?
All right, so welcome everyone, and to the second day. And today we start with Chris Stevens' talk. Chris is a lecturer in the Department of Mathematics and Statistics at the University of Canterbury in New Zealand, and his research is focused on mathematical and numerical general relativity. We particularly thank him for being so late in London and being willing to do this talk with us. And before we start, one thing. Today's talk by Astrid Lamberts is scheduled at 5 p.m., right?
5 p.m. Australian time, yes.
5 p.m. Australian time. Thank you.
Yeah, Australian Eastern time.
Yeah. Okay, Chris, that's on you now.
All right. Well, hi everyone. So yeah, apologies about the time thing. But yeah, I had a different time in mind than what came up. But you know, partly this is my fault for deciding to go to London during an Australasian conference. So anyway, so what I wanted to talk about was a different way of looking at a numerically evolving spacetimes from the point of view of being able to access global quantities that are defined at infinity, which will be explained in more detail as we go on. So the talk is based upon an initial boundary value problem that Jörg and I set up and have been using to look at different applications. Alex Goodenbar just finished his master's looking at the Newman-Penrose constants that were through this formalism. And Merlin, Lachlan, Ollie, and Sebi are looking at different things currently in this formalism. So I thought it would make sense to include them. So I wanted to mainly focus on the background and how why this is interesting and important, why or how we actually implement these things, rather than skipping over some of the details and then going straight to the applications. I thought it might be worthwhile to spend a little bit more time in the derivation of these things, so you can have a sort of a solid understanding of you know the interest of doing this. So I'll give you, to start with, an overview of how we derive or how where the motivation came from for this conformal compactification, looking at sort of an unambiguous notion of gravitational radiation and energies of or momentum of space-time. As you know, that in general relativity, no one yet knows how to locally classify energy, momentum, and things in a well-defined way. And so one needs to look at a global perspective to get that in a well-defined manner. Once we've looked at this conformal compactification and things, we'll set up an initial boundary value problem for the resulting equations that we'll derive, and look at some applications. Firstly, through curvature oscillations. So essentially what we'll do is we'll have a black hole. We will use the initial boundary value problem, choosing boundary conditions in an appropriate way. We'll shoot a gravitational wave into the black hole. which will make it wobble about a bit. And this is in a completely non-linear regime. There's no linearizations or anything going on. And we'll look and see what the resulting curvature oscillations do. So when you excite a black hole, they release quasi-normal modes in the form of gravitational waves, which are ripples in the curvature. And so we look at this from a global perspective. So that's something that's a new application that we've done this year. And the stuff that Alex did was we look at these very mysterious-ish Newman-Penrose constants, which are physically relevant constants that are defined at infinity, that no one really knows what they are in the general case, which is quite interesting. So we managed to compute, as far as we're aware, the first numerical calculations of these in an arbitrary space-time. So I'll give you a bit of an overview of that as well, and then discuss some of the many things that I wanted to do with this formalism, and that's what some of these students are working on. All right, so just to solidify what we're working with, we are obviously using the Einstein field equation, which relates geometry on the left-hand side to energy momentum on the right-hand side. And I can skip over this since we're all doing something similar, I guess. So what we really want is we want the metric of the space-time. So that, given the metric, you can compute the curvature, and it describes the geometry. This, in general, will become a system of coupled nonlinear PDEs, which are in general very hard to solve. For us, we will be looking at numerical solutions. Exact solutions for the cases that we're interested in are just untractable. Right? So we're also going to be assuming that there is no energy momentum on the right-hand side, so we're in vacuum. So that's basically sets up the situation that we're wanting to describe. Now, what the problem is, if we're wanting to find, say, the total energy of the system, right? If you were in Newtonian physics, which I think I've said this on the next slide, yeah, you would just add up individual masses. You have, your particles or masses or whatever that are doing some dynamics on a fixed background, right? So in order to get the total energy, for example, or total mass, you would just look at the particles. But the problem taking that over to the relativity is that the energy momentum of the particles, for example, will change the background. And further, the gravitational waves carry energy. We know this from Bondi, Sachs, and all of these guys in the 1960s that did these series of papers that showed that indeed, if you have a radiating system, so you have some sort of, say, a binary black hole system that's releasing gravitational radiation, then you will find that indeed the mass or energy will decrease through these outgoing gravitational waves. So that appears in the curvature side, so in the geometry. But the geometry is, so you can't. How do you then untangle the geometry with the energy from the waves to a fixed background, like in Newtonian physics? Well, you can't do that in general locally. So it turns out that if you set up what's called an isolated system, so if you did have this system of two black holes orbiting each other in an otherwise empty universe, then what happens is if you go infinitely far away, then all the gravitational radiation will die off, and so on, and you are left with the same manifold or the same metric at infinity. And in this sense, you have a common ground with which to compare different systems, but also you have a way of essentially decoupling the gravitational radiation in particular from with a fixed, or having it with a fixed background, because even though the metric is the same, asymptotically flat, which I'll explain in a second, you have that the rates at which fields drop off are the important bits that represent these differences in the radiation and so on. So it seems then that if we want to look at these notions of energy or even gravitational radiation properly, we need to get to infinity. And the obvious place to look is this isolated sort of regime. So Penrose in the 60s did a lot of work on this, and it published 3 in particular very, very groundbreaking papers looking at, well, Bondi and Sachs and so on in the 60s. They were looking at expansions in 1/r, which was an assumption that was made that is still debated as to whether that is too restrictive or not. But assuming you can do these 1/r expansions out to infinity, then you can look at it in the limit as r goes to infinity and so on, and the coefficients of the expansion give interesting information. So what Penrose did, and that also depends on coordinates, right? What is r? It's a coordinate. You've already fixed your coordinates in some way. Penrose did another thing, which is if you had a manifold that was R4, so it's infinite in all directions, and you did a conformal rescaling. So what this is you take your metric, you multiply it by some positive function squared, you get a new one. And the idea here is that you're multiplying the metric with the function out the front. So you're sort of uniformly scaling all directions. So you're not changing the angles, but what you're doing is you're changing the distances. That this is the inner product that G gives you represents distances, and you're rescaling it in such a way that you bring infinity into a finite picture with respect to this new metric that you obtain. And so he did this for Minkowski space, and he basically said, well, when omega is equal to 0, that would correspond to infinity of the physical space-time that you're compactifying, which of course is not in the infinity. The points at infinity is not in the physical space-time, right? So we have these sort of this point set representing this boundary, this conformal boundary, and it can be thought of as the endpoints of different curves in the physical space-time, null geodesics, space-like, and timeline. And in particular, the endpoint of all null geodesics of the space-time looks like a light cone from some point at infinity. So it looks something like this, which I've grabbed from Penrose's original paper. So what you have is you have this spinning top shape where the boundary of the spinning top, so the outer shell, is the points at infinity. So that's part only of the conformal space-time. Everything inside represents the physical space-time. And for example, if I had an observer, can you see my arrow?
Yep.
Like this? Okay, cool.
Yeah, we can.
Because that would be, otherwise this, cool. Okay, so suppose you had an observer in here and he was or she was traveling in a time-like direction, then what happens is they would always end up at this point here, I plus. This represents the end of all time-like observers. All go to this one point here. Space-like, it's a little bit harder to see, but we go to this edge, this circular edge here that sort of represents the intersection of these two cones, which is really one point. It's a little bit weird. So if you look at the topology on the left-hand side here, it really is just a point, just like I plus and I minus if you are an observer, a time-like observer going into the past. And if you are a light ray, and in this picture, you're going at 45 degrees, you end up on the spinning top sort of, yeah. And so topologically, we have that the spinning top, whether it's in the future or the past, is topologically R cross S2. So you have some sort of cylindrical thing. And these three other points representing time and space-like infinities are just points. So the notion of looking at asymptotics in an isolated system is now a problem of looking at this structure here. And this is sort of the really nice thought of Penrose, was that we should look at this structure. So just to give a bit of a definition, a bit more technical, is that, so what do we mean by asymptotically simple? So this sort of is a way of classifying spacetimes from an isolated system. So if we have a spacetime here and it's asymptotically simple, so this spacetime with the twiddles usually represents the physical one that you're interested in, with the no twiddles or anything on top. That's the conformal spacetime. So firstly, we want our physical manifold to be an open submanifold of this conformal one. So if you can sort of colloquially think of this conformal manifold as being larger in some sense, and then a submanifold of that is the physical one. All right. And so then that's obviously going to be an open submanifold because the points at infinity of the physical manifold are not there, right? It's open. So the boundary of this open submanifold we call scry. So that would be the spinning top sort of thing. That would be sort of the boundary of this is the thing that we're interested in. And nicely, if you're looking at the conformal spacetime, the boundary here is just another point set, right? It's nothing to do with infinity with respect to the conformal spacetime. So you can do local differential geometry rather than limiting processes out to infinity that make it quite advantageous. There exists a conformal factor so that we can conformally rescale the physical metric to get the conformal one. And importantly here, the asymptotic or the conformal boundary is given by the vanishing of this function. And finally, we say that every null geodesic acquires a future and past endpoint. Now this has to be weakened slightly for black hole spacetimes, for example, which is called weakly asymptotically simple. And so the simple here just really means what cosmological constant we have, right? So if it's flat, then the physical Ricci tensor vanishes close to scry. But simple is that this is lambda times g, all right? So that makes, if you have a cosmological constant, then the structure of your conformal boundary is completely different. So at the moment, we're just going to be dealing with asymptotically flat spacetimes, but all the equations that we'll derive actually are valid for any sort of asymptotically simple spacetime. So just to give an actual tangible example of this, the way that we found out the spinning top sort of picture was to take Minkowski space written in polar coordinates. This should hopefully look familiar. And we do some fancy coordinate transformations, which is sort of a way of writing the metric down so that we can do this conformal rescaling to get a well-defined conformal metric. Because at the moment, you know, if we let R go to infinity, this thing's going to blow up. So we need to write it in such a way that if we multiply it by some judiciously chosen function squared, we get a nice metric that is does not blow up at R equals the original R equals infinity. So this coordinate transformation, which is not really important, gives us new coordinates T prime R prime, where we can write this down. So we can write G, which is a conformal metric given like this, is equal to this function times the original G twiddle. So basically we do this coordinate transformation, and then I just write this this down like this. So I figure out, oh well, it turns out that this relationship to this metric is quite simple, and this metric is actually the Einstein static universe, or the Einstein cylinder. That was what Einstein was originally looking at for a cosmological model back when they thought the universe was static. And so it turns out that, well, if we take, you know, this is of the form G is equal to some function squared times G twiddle. So it's apparent from this form that if we take omega to just be this, then we have the G is equal to omega squared G twiddle. And if this is the conformal metric, then this is certainly well defined. And you can, if you had the coordinate transformations, you would see that it's well defined at R equals infinity, and so on. And this gives rise to, this is another representation. This is the light cone at infinity of Penrose. But now I also draw in the conformal space-time to which the physical one is conformally embedded. So this diamond that's wrapped around the cylinder is that light cone at infinity. Space-like infinity is this little point here. Null infinity, which was the sort of the shell of the spinning top, is the boundary here. So we have the this curve I plus and I minus, again are points. So this is sort of, I think, a better way of visualizing what we're doing is everything that here that is drawn with, you know, these vertical lines, all of this stuff, that is the physical space-time. And the conformal boundary is the solid black curve. And with respect to the Einstein cylinder, the solid black curves are just regular points in the space-time. If we have the additional information to say that this is important with respect to something else, but with respect to the Einstein cylinder, it is just regular points, and finite or local differential geometry can be used to study that and figure out some of this global information. All right, so if we're wanting to look at the Einstein equations with respect to this conformal space-time, the Einstein equations are obviously written with respect to the physical space-time. So is there a way to represent them in this conformal picture in a regular way? So can we extend them from the physical space-time to the conformal boundary as well, and essentially move them from G twiddle to G? So can we write the Einstein equations down with respect to everything with respect to the conformal space-time? So a lot of people worked on this. Todd, Friedrich, Penrose, some of the bigger ones, and they'll actually the meetings that I'm attending tomorrow at the Royal Society, which will be cool. So in particular, Friedrich was the one who did most of the work looking at how do we represent the Einstein equations with respect to this conformal spacetime. Now, this is not as simple as you go, well, if we have G and we have G twiddle and we know the relationship between them, then surely we can just take those two spacetimes, compute the Ricci tensors and see how they're related, right? And then just transform the physical Ricci to the conformal Ricci plus other stuff. And then you have the equations with respect to the conformal spacetime. Now, that would be the naive way of doing it. And I mean, if it works, then that would be the way to do it. Unfortunately, it doesn't. So what you find is that if we take the physical Ricci tensor and we write it as the conformal one plus stuff, which will come from the the relationship, namely the conformal factor, you get this. And so, that seems all right until you realize that the whole point of changing the equations to the conformal spacetime is so that you're investigating the conformal boundary in a finite way, but the conformal boundary is at omega equals 0. You kind of see the problem, right? We're dividing by omega. So the naive notion of just writing everything with respect to the conformal spacetime doesn't work. So what Friedrich did in a very non-trivial way was come up with what's called the metric conformal field equations. So these are a regular extension of the Einstein equations to the conformal boundary and in fact beyond, so to this conformal spacetime. So it turns out that the unknowns of the system, so things start to get a bit more intense now, is the conformal metric, the conformal factor, the Skelton tensor. So this is a combination of the Ricci tensor in a particular way. It defines this new quantity S, and we have this conformal rescaling of the Weil tensor. So recall the Weil tensor represents gravitational radiation or the curvature induced by gravitational radiation and things. So this is not induced by matter. This is the part of the curvature that remains when the matter vanishes, the energy momentum tensor vanishes. Now, the reason why we do this sort of scaling is a little bit more technical than what I'm about to say, but the Weil tensor here vanishes at infinity of your isolated system. So in an asymptotically flat spacetime, this vanishes. And so does the conformal factor. All right, so you have sort of a 0 over 0 thing going on here. And this K is sort of the conformal quantity. It's called the gravitational tensor or gravitational spinner if you do spinner stuff. And that is non-zero on the conformal boundary. And this is in fact the thing that will tell us information about the gravitational radiation and energy and so on and so forth. Now, the problem here is that in order to figure out what the conformal structure or the conformal boundary looks like, you need to know what the conformal factor is. But unfortunately here, the conformal factor is a part of the system which you don't know until you solve it. So that's a kind of annoying, especially if you do numerical evolutions, you don't know where the conformal boundary is. So Friedrich continued his studies and said, well, why don't we drop our connection from being metric compatible to a Weil connection? So you recall that metric compatibility is the covariant derivative on the metric is 0. So if we drop that and we have a Weil connection with a hat here, if that acts on, say, the conformal metric, then you get the following here. So you get a class of connections that is fixed by this one form here, F. So if F is 0, we get the metric connection. And if it's non-zero, we get something else. But the point is that choosing a Levi-Civita connection, for example, fixes a metric. which fixes sort of a metric in the conformal class of conformally related metrics. And at the moment, we're wanting to sort of stay away from fixing a particular one and look at the conformal structure as a whole, right? And so this is what Frederick thought about. And what he did was, you know, how do we fix this one form in a way that might sort of help us? And he said, well, we're looking at everything from a sort of a conformal structure point of view. Why don't we look at geodesics in the space-time, but a generalization of geodesics that are independent of which metric you are looking at in a conformal class. So, you know, depending on how we choose our conformal factors, we get a huge range of metrics. So is there a generalization of geodesics that are a property of that structure as a whole rather than one representative? And in fact, this gives rise to what's called conformal geodesics. So we have something that you would sort of hope to see is, you know, the autoparallel aspect. You have the derivative of a vector along itself, but it's no longer equal to 0 or a multiple of itself. It's going to be related to this an extra variable, a one form, and this one form here is going to be related or going to be governed by its own equation. So this one form in particular, B, that could be used to fix a connection, right? Because if you have a one form, then that essentially, if suppose you say B is the one form to which the Weyl connection has when it acts on the physical metric, then you could say, well, why don't we fix it by adapting ourselves to some sort of conformal congruence of conformal geodesics. So this in particular, if B was 0, this would reduce to the standard equations. This one, standard equations for the metric geodesics. So it turns out that if you look at writing down a frame adapted to the these conformal geodesics, you get what's called the generalized conformal field equations. So what these are another set of equations with different unknowns, but we have this Weyl connection coming in. And you think, oh, you know, this is starting to get complicated. Why are we making it more complicated? But what you find, which is quite remarkable, is that when you introduce this extra degree of freedom coming from this Weyl connection, and you fix it by looking at something else coming from the conformal class or a property of the conformal structure, namely conformal geodesics, everything simplifies. It's quite remarkable. And I'm already going very slow, so I won't be able to talk about that. But that, at the end of the day, it's remarkable how simple things become. And you'll laugh at me when I actually show you the equations that they're not simple, but from a conceptual point of view they are. So now we've introduced a particular frame which is going to be adapted to these conformal geodesics. So we have, if we have coordinates x, then these are just the frame coefficients. So the bold index here is just a contraction of this orthonormal frame. So we have frame components that are unknowns. We have the connection coefficients coming from the Weyl connection acting on the frame. We have the Skelton tensor with respect to the Weyl connection, and then we have the K as before. So it's quite different to the metric conformal field equations. But the really nice thing here is that, well, let me talk about this gauge in a little bit more detail first before I mention this. So to clarify, when I say that we adapt to conformal geodesics, what do I mean? So I think about this from a sort of numerical evolution point of view, where you fix an initial surface, you specify data on there, and then the Einstein equations split into evolution and constraint equations. Evolution equations tell you how your data propagates with time. Constraint equations constrain your data on each slice that you have. And if you satisfy these equations on some slice initially, then up to numerical errors, they will be satisfied during this evolution. So initially, if we specify initial data for this U, the tangent to the conformal geodesic, and this one form B, we can specify our orthonormal frame, our time-like frame vector to be tangential to the this time-like conformal geodesic, the spatial ones to be tangent to our surface. We can pick our spatial coordinates as we like on the surface, and that essentially fixes our frame and our coordinates on this initial surface. The question is, how do we extend them in the neighborhood of the surface in 4D? This is when the conformal geodesic equations come in. Well, if we choose our parameter S to be the one that comes about from solving these conformal geodesic equations, so this parameterizes the conformal geodesics. That is a natural time coordinate. We again continue to have our time-like frame vector to be proportional to the tangent vector of these geodesics, and the spatial ones to be orthogonal. And then finally, we say we want our coordinates to be constant, our spatial coordinates to be constant along these conformal geodesics. So that gives us a full 4D frame and coordinates that are adapted to this sort of conformal property. So I think that's all I want to say here. But what you find when you've adapted your frame and your coordinates to this is that taking successive derivatives of your conformal factor, which you don't know yet, this is arbitrary, right? I mean, that's part of the night, you know, you can choose your conformal factor in different ways. If you take 3 derivatives along your conformal geodesic, you find that it's 0. So then integrating back, you find that omega is a quadratic in the parameter along these conformal geodesics. Really, really, really cool. I think Friedrich was very surprised by, when you read his papers that just explain this, he was very surprised that this happened. And it's kind of natural in some sense, because, you know, you saw the light cone at infinity, you have like a plus or minus thing going on, right? And the conformal factor is quadratic if it's got 2, you know, if you find the roots of this and, you know, you have 2 real roots, then it's a, you know, plus or minus thing going on. You have plus and minus infinity. And you can also, he found that another quantity in the system can be felt a priori. And the important thing here is that the conformal factor is fixed based on some initial choice on your initial surface, and then how it extends in time is solely based on initial data for your conformal geodesics. So the initial data for your B and your U, which is really cool. So it's very important to choose a congruence of conformal geodesics in the right way in order to properly extend and maintain this gauge. So that's what Lachlan in particular is working on at the moment. So this becomes all of these, there's a huge amount of PDEs in this system, which I've neglected to show you, but so many of these drop out when you're in this gauge. The resulting system is symmetric hyperbolic, which means that you've got all the nice well-Posedness theorems and so on, and it's very nice. So I really need to hurry up, I hope. Florian at Otago was actually the first one to look at these equations from a numerical perspective. So we have now we have this nice system of equations. We want to solve it numerically, but how do we do that, right? So he looked at de Sitter space, which was with asymptotically simple space-time. It had no boundaries. So de Sitter space, the conformal compactification of that, the spatial slices or time slices are compact. So you don't worry about boundaries. And he was able to do that in spherical symmetry, solve these equations, which was the one and only time that people did this. And Florian was actually a PhD student of Friedrich. The only notion of an initial boundary value problem came from Friedrich again. I'm looking at anti-de Sitter. So anti-de Sitter, it can be embedded into the Einstein cylinder, and it's like if you take a vertical slice through the middle, so it's still infinite in one direction. That is the embedding of the universal cover of anti-de Sitter, if you want to be specific about it. And so you have natural boundaries in that case. And so Friedrich found a well-posed initial boundary value problem formulation where the boundaries were given at these particular points, where you get to go halfway around the cylinder and then stop. And those points where you stop is in fact the conformal boundary of anti-de Sitter. And so it's a very specific boundary. And that was basically the extent to which an initial boundary value problem had been devised. So Jörg and I, quite a few years ago now, we did a more general initial boundary value problem where instead of having the special boundary for anti-de Sitter, we generalized it to say, well, we can have an arbitrary time-like conformal geodesic as your boundary. So that allows this to be used in a much wider perspective. So we can do a lot of different things with this. We write it in what's called the space spinner formalism, but as I'm running out of time very quickly, I'll just skip through that. So we arrive, and this is where I thought you would laugh at me when I said you have simple equations. These are the evolution equations for the system, written abstractly in space spinners. Now, importantly, the curly D here is essentially a time derivative, and the curly D with two indices is, say, a spatial derivative, colloquially. So we only have one system of PDEs here. All of these things are ODEs. All right, so what do we have? We have the frame coefficients. We have the one form that defines the Weil connection. We have quantities that represent the connection coefficients, the capital gamma. We have the Schouten tensor coming from the Weil connection. And this thing is the K. This is the important thing that represents the gravitational radiation. So importantly, it is this thing that is the PDE of this. This is the only place that the partial differential equations come from. And then below the horizontal line, we have stuff that is known a priori. So these equations, given initial data, propagate with time. Tell us how this data propagates with time. And we have constraint equations. So these are in particular only involving spatial derivatives, and these must be satisfied on each time slice. Now, the reason why I highlight this one is because this is the very important one when it comes to imposing boundary conditions. So I'll just skip that just because we've got, yeah. Okay, so let's show you some applications. So just to summarize, we have now taken the Einstein equations defined in the physical spacetime. We've done a regular extension to some sort of conformal spacetime. We have set up an initial boundary value problem, written down the equations, adapted to, all this nice stuff for the point of being able to do numerical evolutions and in very general situations and seeing what happens at the conformal boundary. So this is Schwarzschild. So this is the conformal compactification of Schwarzschild, where this piece here is essentially the light cone at infinity that you've been looking at, but now we have extra piece that represents the singularity, and the dashed line is the event horizon. So this is the maximal analytic extension where you have a double copy coming through critical Zacharias coordinates. So what we want to do is we want to shoot a gravitational wave at this black hole. So first we use exact Schwarzschild initial data on some slice. Now, we don't compactify out to spatial infinity, although Ollie is working on that at the moment, just because that has its own problems. Salva, I'm sure you agree that this is a bit scary. So we ignore that for the moment. And what we really want to know is what happens on future null infinity up here. So if I was doing a standard evolution, numerical evolution in physical space-time, my outer boundary is going to be time-like. So it's going to end up at I+. Right, so it's going to look something like that. You're going to completely miss this. And this is what people do, binary black hole evolutions and so on. They don't actually get to Scri+, where the gravitational waveform is well defined. They have to do some sort of extrapolation and other procedures to approximate it. Is what we do is we can go right through, because this is a sub-manifold of the conformal manifold. So we can go right through, we can obtain Scri+ in our computational domain, and we can go to infinity and beyond. So that's really an advantage of the conformal field equations. And I do something a little bit more advanced, is that bad things tend to happen if you go far away from Scri+ outside. And also, I don't want to hit the singularity. If you can imagine, bad things happen also there. So if we go inside the event horizon, outside Scri+, we can just chop off the computational domain and track it along, just to avoid bad things happening on the boundaries. So the idea is that we choose our boundary data here to impose a gravitational wave that will propagate in. It'll interact with the black hole. Gravitational waves will be released through curvature oscillations, and they will hit Scri+, and that's where we can compute them. So that's essentially what I've said there. We use Coffee, which is a Python package developed at the University of Otago that contains all necessary numerical schemes to get this working. So we have Runge-Kutta to integrate with time. We have finite differencing in radial direction. We have spin-weighted spherical harmonics in the angular direction. And this is parallelized through MPI and OpenMP. So it's even though it's written in Python, it's been optimized quite well. So we've done a lot of studies on this to make sure it works, because as you can imagine, by looking at the equations, it will be very easy to screw this up. And one of the later checks we did was we confirmed the Bondi-Sachs mass loss along Scri+ to 10 to the minus 9, which is, I think, quite good. So that basically is just saying that if you had a certain you were at a certain point on null infinity, and your system was radiating gravitational radiation, then if you compared your, say, total mass on a light cone that goes out to null infinity at 2 times, that the difference on that is proportional or is equal to, just using the generalized Stokes theorem, the integral of a certain quantity in the volume between. and that volume is 0 if you have no gravitational radiation. So M1 is equal to M2. But if you have gravitational radiation, that integral you can kind of see here on the vertical here is the News function n times its conjugate, which is of course positive. So basically, the point of that is saying that the difference is going to be decreasing if you have gravitational radiation. So that was the Bondi-Sachs mass loss. So I won't go into that in too much detail, but we're confident our system works. I won't be able to do that. So let me show you this picture, which is something, and I'll try and stop. I'll stop at 12:55 my time. What we're doing here is this is Scribe plus. The green line is the event or the apparent horizon. The purple are just Schwarzschild R equals constant curves, and I'm plotting the ingoing gravitational radiation. So you can see that here I introduce a wave on the boundary. It comes in, it gets swallowed by the black hole, but then afterwards you're seeing some sort of oscillation appearing in the curvature. Now this is, if we're in the linear regime, this is what's called the quasi-normal ringing. So what we find is that the curvature wobbles about when you excite the black hole by hitting it with a gravitational wave. And this goes all the way out to Scribe plus, where we can read off the oscillations there. And further to linear theory, which basically looks at stationary boundary value problems on certain slices that start at the horizon. We can look at oscillations inside the horizon as well, which is quite cool. So we found, which is pretty amazing. So we do this in the non-linear regime, and the wave that we put in is got a it's the amplitude is 10 that we choose. So I mean, if it's certainly not linearized, right? You square that and it's not going to be negligible. So amazingly, sort of what we found was that if we look at those curvature oscillations and we look at the frequency of those, they should match the frequency of the linear theory if we look far enough in time once things settle down. But even after the first couple of oscillations, we see that comparing to the linear frequency, even here, these are only half periods, each of these columns that we approximate the frequency. This is already within 0.1% of the linear prediction, which is quite amazing. There are others that are excited that are not as close, but the fundamental ones where the mode that comes in, this is the corresponding, the L equals 4 corresponds to the wave that came in, is very close. These ones are the non-linearly excited ones that do take a bit longer to settle down. But that's quite remarkable how quickly a perturbed black hole, a non-linearly perturbed black hole, can be represented by the linear theory. So that was in a new paper that's just been accepted. I won't talk about that. The last thing I wanted to talk about was what Alex did, and apologies to Alex because I've got about a minute to explain what he did last year. But what's really cool is if you take a slice of null infinity, which is topologically a sphere, we won't have a unit sphere, we'll have, I like to say, a potato. It's going to be a wiggly sphere. You do a particular integral around that sphere, namely something that looks like that, which might be a bit scary, but that's what it is. You do an integral of this thing, and you find that that is completely conserved, independent of which cut you take of Scribe plus. You do this integral, you're going to get the same. Well, there's 5 choices for you, so you're going to get 5 numbers. These 5 complex numbers do not change no matter which slice you take, and no matter whether your space-time is dynamical and it's wobbling about, whatever. These numbers are going to remain the same. Now, this is also conformally invariant, these are physical quantities. And if you're in a stationary space-time, then you can write it in terms of the multipole moments, because you can do these multipole expansions out to spatial infinity if your space-time is stationary. So it's related to, you know, quadrupole, dipole, angular momentum, and so on. But stationary space-times are kind of boring. You know, the one that we had is certainly not stationary. Is there, you know, can we say anything about this? Well, no one knows what the physical interpretation of these numbers are in a general space-time. So Alex, and this is in a paper that's been submitted to CQG, we certainly found that this error here is basically, as we increase our resolution, the difference in these numbers as you go along, so you keep computing them in different cuts as you evolve, and you see how much they differ from the initial cut. So it should be 0. We do a convergence test and we find it's converging to 0. So we find that indeed up to numerical precision that we're working with, these numbers are conserved. Let me just say, the last one here is Alex also did a fully 4-dimensional, I can't emphasize enough how cool this is. We have done no symmetry assumptions, no linearizations, it's no assumptions at all in full 4 dimensions. So we've put in a gravitational wave, the black hole's wobbled, and we read these out at infinity. And these are the 5 numbers as we increase the amplitude of our wave. And so they do, some of these are overlapping, which is why you can't sort of see 5 different things, but they are certainly non-trivial, and this is them individually. And so this is the first time that that this has been, these have been computed in any numerical regime. And the question now that we want to look at is, if we can, play around with these things, can we figure out what these numbers mean physically, and whether they give us information about the space-time that is of use, and before we even start, getting into, it could be that we read off these numbers just well before 2 black holes collide, and that might tell us information about something after the collision before we even get there. Who knows? That's, these were developed in the 60s, and still no one really knows what they are, which is quite interesting. So I'll leave it there. I'll just plug the fact that I have a 2-year postdoc position that I'm looking for a student or a PhD student that's recently completed to work on this sort of stuff. And this is what Sibi, Merlin, Ollie, and Lachlan are working on at the moment. And this is just a bunch of different things that I would like to do. And in particular, set up a full scattering problem for gravitational waves, which is what these guys are working on. But I thought I would just advertise that here. Yeah, so that's all. So please, if you've got any questions or whatever, fire away.
Thank you, Chris, for this. It was really in-depth overview. Thank you very much. Are there any questions? Because I have a ton in case. So just feel free to unmute yourself if you have any question.
Hi. Can you go back to the conformal diagram?
This one?
Yeah, this one. Is there the wave across the horizon? to the black hole?
Yeah, so the black hole apparent
Yeah.
horizon is essentially this. Well, we're in this
Yes.
universe, so here, and what's really cool in the conformal diagram here is that, you know, light rays are 45 degrees and time-like observers are within those. So as soon as an observer goes inside this apparent horizon, r equals 0 is in their future, right? It's a nice sort of conceptual way of representing what happens when you go into a black hole.
Yeah. How to calculate the Conformal modes according to this diagram? What's the boundary conditions about this?
Yes, so quasi-normal modes are something that another one of my students, Jack Aim, is working on. So these are linear perturbations of a black hole spacetime. So what you do in general, well, there are lots of different ways. Reg, Wheeler, and Zarelli did these with respect to one formalism. Tucholsky did it with respect to the Newman-Penrose formalism. But essentially, you do a linear perturbation, and you find that the modes that I'm thinking from the Tucholsky point of view that represent the outgoing gravitational radiation is decoupled from the other perturbations. So you get a second order PDE for your outgoing gravitational radiation that only involves background quantities from, say, the Schwarzschild spacetime, if that's what you're looking at, not spinning, not curved. And the boundary conditions, you have one at the horizon and you have one at infinity. And the boundary conditions basically say, I don't want my gravitational waves to be coming out of the horizon, and I don't want my gravitational waves to be coming in from infinity.
Right.
And those are the boundary conditions. And once you've specified those, then you've got a fixed boundary value problem to solve.
Okay, thank you.
Is there any other question? So I have one. Can you please elaborate on what like your student is doing at Space Like Infinity? You were saying that someone was working.
Yes.
Like really quickly,
Yes.
dive into you do like a golden node. Maybe you can send
Yeah.
me some work that is being done. But anyway, in this framework, if you can just give some introduction to that.
Yeah, so I mean, so what we're looking at is the linearized conformal field equations around the cylinder. So this is very similar to what George did with Jörg in his PhD. So the problem is that I naught is in general singular when your space-time has mass. And even in Minkowski space, it has issues. And it's really hard not to, you know, this is a hard question to simplify, but what happens here is that Friedrich has the conceptual idea of blowing up this point to a cylinder, and the tops of the cylinder, and this is perhaps more relevant from this point of view. If you imagine this point here being a cylinder, and that cylinder connects to scry plus here and scry minus here, that is a way of looking at regularity of solutions and things like that globally. And when the cylinder that is now I naught touches the top of this set here, the bottom of scry plus or the top of scry minus, the PDEs that govern the propagation of the Weyl curvature, basically they become they lose positive definiteness. So that means that hyperbolicity goes out the window, and you can't mathematically evolve them anymore. You can't solve them anymore because you essentially can't invert the functions that are in front of the dt terms to get dt equals. So what we're looking at is we're looking at a compactification that compactifies to the cylinder, and in the linearized case, and we're wanting to look at seeing how the numerically how the data propagates up to these critical sets, and what happens to the simulation when this bad mathematical thing happens. So George has already done this, but what we're looking at from the point of view is to see if there are ways to extend beyond that. And from a mathematical point of view, that doesn't exist yet. But from a numerical point of view, there's only been that one investigation. And if we want to look at the full scattering of gravitational radiation, or a numerical evolution that contains the entire conformal boundary, then this is a problem that must be dealt with. So Ollie is looking at the linearized case to start with around the cylinder at spatial infinity, to see whether we can do anything to get past the critical sets of the spatial infinity cylinder and continue on to Scribe Plus.
That's incredibly helpful. Thank you very much for this. All right. If there are no more questions, then I think we can let Chris go to sleep. And and we'll recollect at 11 for Volker Schlew talk. So yeah, thank you very much, Chris, and I'll see all of us later. Thank you.
Thanks, Salva, and I hope that was useful. And
Absolutely.
thank you to the organizers for inviting me to give this talk.
Absolutely. If you can send me some reference about this, I will appreciate it, but that's beyond the scope of this talk.
Yeah, sure, we'll do.
Thank you.
Thank you.
All right.
Night.
See you everyone.
Bye.